Hello, welcome back to Essentials of Computer Architecture and Organization. We're continuing on the last section within Coomer. Last time we talked about parallelism, and now we're going to be talking about something called data pipelining. And so data pipeline is so let's introduce what that concept means. And so it's one of two major optimization techniques. So the information flows through a series of stages, processing components. And so each stage can perform arbitrary operations on the data. It can inspect, it can interpret, it can modify it as it's going through that pipeline. And so here is a kind of an example of how that might look for an illustration of a pipeline. And for the MIPS architecture, this is something that you guys might be familiar and have seen that. So what are some of the data pipeline possibilities? You can have hardware or software implementation. You can either have large or small scale. It can either be synchronous or asynchronous flow. It can either be buffered or unbuffered. It can have finite chunks or continuous bit streams. It can have automatic data feeds or manual data feeds, serial or parallel data between the stages, and homogeneous or heterogeneous stages. So basically, just by reading through that, there's a huge set of possibilities that exist. So in terms of the software implementation of data pipelining, this was popularized by the Unix command interpreter. And so if you've ever done command line programming, this is where this would come into play. So the user can specify a pipe as a command. So this character here is a pipe. So here's an example of aggregating 4 command line commands together, and to take cat, so you're listing everything. You then do some editing manipulation within that second form of manipulation, and then you have how much is going to be shown. So something that would fit into a screen, and then you can push the space bar to continue or something like that. So it substitutes partner for friend, deletes words that contain W, and passes the result to more for display. So this note that examples can be optimized by swapping the order of the 2 said commands. So what about implementation of a software pipeline? And so for a uniprocessor, each stage is a processor or thread. For multiprocessors, each stage executes on one separate processor or core, and the hardware assist can speed interstage data transfer. What about hardware implementation of data pipelines? So there are 2 basic types. You can either have an instruction pipeline or data pipeline. So for instruction pipeline, this was covered early in the course, and the goal is to try and optimize performance, and it's used heavily with RISC architecture. We talked about some examples of processors that fall into that. Reduced instruction set computing. The MIPS architecture is an example of that. So each instruction process is in stage, and so it's a pipeline. This is a very apropos word. It goes from one to another, like I showed in that graphic a few slides ago, what you saw here. So that's what we're seeing in this. And so the exact details and number of stages depends on the instruction set and the operating type. And the other one is a data pipeline, and this is relatively speaking, a new idea. So what is a hardware data pipeline? It's a sequence of data items passed through the pipeline. Each stage performs computation on the data item and passes items to the next stage. It requires the designer to divide computations into stages, and it's among the most interesting uses of pipelining. So how does performance, what does it look like with data pipelining? A data pipeline implemented with hardware can dramatically increase performance, the throughput. to see why, let's consider an example. Think about an internet router handling packets, and then we can assume that a packet processes one packet at a time and then performs 6 functions on each packet. So here's an example of an internet router processing. As first it receives a packet, verifies, checks for forwarding, selects a path, prepares for transmission, and transmits the packet. So those are the things that need to be done. And so here's an illustration of a process in a router and the algorithm used. And so we have an input from the network. We have this processor, and then it has to do one of several things based on what the processor interprets is the meaning of what to do. So, and there's a infinite loop that is constantly doing this. And so for A, it's an illustration of an internet router. Multiple connections go into the output. So one to many, and the computational step the router must take for each packet. So goes in, and then it has to determine which of these outputs that data is supposed to go out. So how about, let's consider an example of a data pipeline implementation. So here we have this kind of a block diagram. We verify, check for loops, select the path, prepare for transmission, and then it exits. And so this is a graphical representation of that basic flow. So we can imagine a passing through the pipeline. And for now, assume that there's 0 delay between the stages. And a question to consider is, how long will the pipeline take to process the packet? The answer is the same amount of time as a conventional router. So the news about pipelines, the bad news, if it uses processors of the same speed as a non-pipeline architecture, the data pipeline will improve the overall time necessary to process a given data item. So that's the bad news. The good news is, by overlapping computations on multiple items, a pipeline increases throughput. So what about data pipelining and the improvement of throughput? It is possible to partition processing into independent stages. The overhead required to move data from one stage to another is insignificant, and the slowest stage of a pipeline is faster than a single processor. So let's explore a little bit about understanding pipelining speed. And so we want to assume that the task is packet processing. The processing a packet requires exactly 500 instructions, and the processor executes 10 instructions per second. So the total time required for one packet would be 50 microseconds. And so the throughput for a non-pipeline system would be 20,000 packets per second. I'm not going to go through the math, but just try and have a higher level survey as we go through this. So let's continue this and suppose that the problem can be divided into 4 stages. Require 50 instructions, 100, 200, and 150. The slowest stage takes 200 instructions, and the total time required for the slowest stage is 20 microseconds. So the important principle is the throughput of the data pipeline is limited by the slowest stage. So the overall throughput is 50,000 packets per second. And note that the throughput of a pipeline version is 250% of the throughput of the non-pipeline version. So what about pipeline architectures? The term refers to computer systems in which the primary focus is data pipelining. Most often it is used for special purpose systems. The data pipeline usually is organized around functions, and it's less relevant to general purpose computers. So what about the functional organization of a data pipeline? We build one pipeline stage per function. And so here is a little bit of how that might look. And so for A, we show a single processor handling 3 functions versus showing a process divided into 3 pipelines where each one handles one of them. So this has a functional decomposition. So each one is doing one thing versus one thing doing 3 things. So a couple terms for pipelining, you have setup time, stall time, and flush time. So set time refers to the time required to start the pipeline initially. The stall time refers to the time required to restart the pipeline after a stage blocks to wait for a previous stage. And the flush time refers to the time that elapses between the cessation of input and the final data item emerging through the pipeline. What about something called superpipelining? It's most often used with instruction pipelining, and it subdivides a stage into smaller stages. So an example is subdivide an operand processing into operand decode, fetch immediate value or value from the register, fetch value from memory, fetch indirect operand, and the technique is to subdivide the slowest pipeline stage. So in summary, pipelining is a broad fundamental concept, can be used with hardware or software, and applies to instructions or data. It can be synchronous or asynchronous, and it can be buffered or unbuffered. In terms of pipeline performance, unless faster processors are used, data pipelining does not decrease the overall time required to process a single data item. Using a pipeline does increase the overall throughput, the items processed per second, and the stage of a pipeline that requires the most time to process an item limits the throughput of the pipeline. So thank you very much.